Here's the interpretation. Here's your wave function for v equals 2. You got, is this v equals 2 or v equals 1? You got one known, so this is v equals 1. Right? What's the most probable location of the particle? What's the interpretation of, how do we interpret psi? The square of psi is a probability density. So if you plot psi squared, if you square this psi, this is the square of psi, right? What's the most probable location of the particle? Right around here and over here. And here's a visual representation of that. Where this thing is thickest, that's your highest probable, most probable location. And what happens here at the origin? Okay, see there, there's a node right there. When you have a node, the probability of finding the particle there is 0. Okay, so how is this different from the classical prediction? Okay, classical prediction always says the most probable location is at the turning points, right? And one thing you'll find is if you try to calculate where the turning points for this, it's not going to be here and here. It's a little bit past that one. Okay? And we'll see how we can calculate the classical turning points in just a little while. Here's another way of looking at the wave functions. This is for v equals 0, 1, 2, there's 3, up to 20. Okay? This is the square of the wave function. Notice it doesn't go down. Okay? So this is the function squared, wave function squared. What's happening as you go from v equals 0 to v equals 20? As you go to higher v, the most probable location spreads out towards the end, towards the sides, right? Closer to the classical turning point. You're approaching what's called the classical limit. So as v gets really, really high, these high probable, most probable locations would be closer to the classical turning points. So how would you calculate these properties? What's the average location of your particle? What integral would you have to write? Psi x psi, right? So this is going to be integral of psi star x times psi dx from negative infinity to infinity. Just plug in the functions. And if you did this, if you were to calculate the average potential energy, you'll find it's just going to be 1/2 of the energy. What's the energy? V plus 1/2 h nu. And you'll find that the average kinetic energy is also going to be 1/2 of the energy. Okay, so how would I solve for the average potential energy? What would I have to do? What integral would I have to write? Whatever psi is, I take its complex conjugate, right? And what's the potential energy operator? It's 1/2 kx squared. Multiply that with psi and integrate over all space. So from x equals negative infinity to x equals positive infinity. Okay. Now one thing you'll find is, if you remember, the classical description says your particle with a given energy is just going to go from one turning point to the other, right? From plus A to negative A and back. Okay. One thing you'll find is if you plot psi squared, you'll see that psi squared, in fact, has a finite value beyond the classical points, the classical turning points. So we say that our harmonic oscillator can actually tunnel through a potential barrier. So there's a probability of finding your oscillator, your particle, beyond the classical turning points. All right, so how do we determine the classical turning points? If x sub Tp is a classical turning point, how would you solve for that? What was our energy? 1/2. Oops, sorry. It's V plus 1/2 times h nu, right? Well, that's the quantum mechanical prediction. Classical mechanics says, what's the energy? 1/2 k x squared, and we're going to use x sub tp here as our turning point, so x sub tp squared. This is what we called A earlier. Okay, so this is the classical mechanical energy, this is the quantum mechanical energy. So how am I going to calculate for a given allowed energy level? How am I going to calculate the classical turning point? I'm just equating those. I'm just going to equate those two. What do you get? 1/2 k times x turning point squared equals v plus 1/2. Oops, that should be h nu. H nu. So solve for the turning point. That would be equal to v plus 1/2 h nu times 2 divided by k, and then take the square root of the whole thing, right? So your plus or minus, right? So your classical turning point is plus or minus square root of v 2 times v plus 1/2 h nu over k. Right? Those would be your classical turning points. And what you'll find, okay, you can show that the value of y at the classical turning point, what did we say y was? That was just going to be x over alpha, right? It can be shown that that turning point is just going to be square root of 2v plus 1. And what you'll find is for v equals 0, if you did the integration, you'll find that beyond the classical turning points, the probability of finding the particle is 16%. Okay, so classical mechanics says beyond the turning points, you can't find the particle, right? So 0 probability of finding the particle beyond the turning points. Quantum mechanics says no, there's a 16% chance if v is 0. If v equals 6, there's a 7% chance. Generally what happens is at high v, that probability drops. Okay, so again, you see this pattern where it seems to approach the classical limit as you go to higher v. So the most probable locations tends to spread out towards the classical turning points at high v levels, and the probability of the particle being able to tunnel beyond the classical turning points drops as you go to higher and higher quantum numbers.